Okay. Now we have next speaker, Martin Sasieta, is going to talk about ER for typical EPR.
Okay, thank you very much to everyone for coming, and thanks for the invitation. Also, thanks to the organizers for putting up this really nice conference here. I'm really having a great time. So today I'm going to change topics a little bit to, from what Irene has told us, and I will essentially talk about black holes. Okay? Okay, so everything that I'm going to say today is going to be based on these two papers that came out earlier this year in collaboration with Javier Magán, who's at the Instituto Balseiro in Argentina, and with Brian Swingle, who is at Brandeis. Okay. Okay. So let me start by giving you a broad motivation to why we are interested in this kind of problem. So in ADS-CFT and in general in holography, there are two ideas that have appeared over the last decade or so, which appear to be in tension. Okay, one is famously known as ER equals EPR, and I'm sure like all of you have heard about this slogan before. Essentially, the idea is that enough microscopic entanglement between two holographic quantum systems generates some notion of an emergent space. Okay. So this is, of course, best understood for quantum systems that describe black holes, in which case if you start with two black holes which are entangled, they're entangled enough, what emerges, the space that emerges is essentially the black hole interior. Okay. So the classic example in holography to try to understand this is to place two holographic systems here on the left and on the right on this specific quantum state, quantum pure state, okay, which is entangled. So this state is called the thermophile double state, and it is a very special entangled state in that it canonically purifies the thermal state on one of the two systems. So this state contains a large number of EPR pairs, so it contains a large number a large amount of entanglement. And the point is that this state is semi-classically dual to the eternal black hole in ADS. So more precisely, what this means is that the semi-classical dual to this microscopic state lives on some Cauchy slice of this bulk geometry. The point is that this Cauchy slice is connected between the two ADS asymptotic boundaries. So the spatial connectivity of the semi-classical dual to this state essentially comes from the amount of entanglement of this state. Okay, that's sort of the general idea. So the second idea, which appears to be in tension with this one, is that the thermophile double example or other situations, which are sort of simple, they are very fine-tuned, and they are not generic examples of entangled states between two black holes. So in particular, there's been arguments over the past saying that perhaps a generic entangled state of the two black holes doesn't have an interior, and it perhaps contains some non-perturbative object that you can call a firewall or something else that nobody knows how to describe. So as you see, this kind of idea is sort of against the mantra of ER equals EPR. So the question we want to try to understand is whether more generic entangled states of two black holes have semi-classical interiors or not. Okay, whether generic EPRs of two black holes have ERs associated to them. Okay, so let me, in order to define what I mean by typical or generic entangled state, let me start by illustrating the definition in the simplest case, which is a collection of n qubits at infinite temperature. So if we just take two such systems, so we took two collections of n qubits, and just consider maximally entangled states, we will generate some collection of states, which I'm here referring to as EPR. Okay? So this is essentially a set within the Hilbert space of the two systems of qubits. It's a subset of states. And the infinite temperature thermophile double is one such state. So in particular, the infinite temperature thermophile double has this particular wave function in the energy basis. So you see that it's diagonal. These i's are the energy eigenstates of some Hamiltonian. And one property is that the wave function is diagonal, and it, moreover, doesn't contain any phases. Okay. So this is a canonical purification of a thermal state in the sense that if you compute the reduced density matrix to one of the two systems of qubits, you get a maximally mixed state, which is the infinite temperature Gibbs state. So a typical EPR is essentially a generic point in this set. So the thermal field level is not very non-generic. Okay? So in order to define generic, you need to specify some measure. And the natural measure that is sort of inherited from the natural measure in the space of unitaries is essentially the Haar measure. Okay? So essentially the point is that a typical EPR can be constructed by applying some random unitary to one of the two systems in the infinite temperature thermal field double. And this will land us in a generic point in this set. So if you diagonalize the wave function of a typical EPR, it looks pretty much like the infinite temperature thermal field double, but now you get a collection of phases, and moreover, the eigenvectors are different from the energy eigenstates. They are other vectors that essentially correspond to the eigenvectors of the unitary that you use to create the state. So a typical EPR can equivalently be defined by a statistical distribution of phases and a statistical distribution of eigenvectors. Okay? In particular, for a typical EPR, the eigenvectors are uniform random states in Hilbert space, and the eigenphases are distributed in a very particular way. They are distributed according to the circular unitary ensemble, which is a famous ensemble in random matrix theory. Okay? So for us, the important property is that if you just focus on the wave function of a typical EPR, the nearby eigenphases tend to statistically repel each other. And one can see this empirically just by taking some high dimension unitary and plotting the eigenphases of this unitary on the unit circle. And with this information, one can make a histogram of the eigenphase separation between the nearby eigenphases. And you see, statistically, nearby eigenphases are correlated in such a way that it's very unlikely for them to be close to each other. So in this sense, they repel each other. So this is a defining property of the CUE. And as you see, the infinite temperature thermal field double is very atypical because all of the eigenphases are essentially zero. Okay, so the argument by Marov and Polchinski was essentially that typical EPRs, like this state that I wrote here, they have the same entanglement as the infinite temperature thermal field double, in that if you compute the reduced density matrix to one of the two sides, it gives you an infinite temperature density matrix. However, if you want to compute a correlation function between left and right system in a typical EPR for a simple operator, say a local operator, the value of this correlation function is typically exponentially small in the entropy of the system, and moreover, it very erratically depends on the specific microstate that you chose, the specific phases of the wave function and eigenvectors of the typical EPR. And so this signal is very erratic and exponentially small, and therefore they argued that this was enough to conclude that it cannot be reproduced semi-classically. So there must be something very quantum gravitational for a typical EPR of two black holes. That was the sort of argument. So in this talk, I will try to argue that this is not the case by very explicitly constructing families of Einstein-Rosen bridges, so black hole interiors, which incorporate this erraticity semi-classically, which provide a window into the generic structure of the Hilbert space of two black holes in any theory which contains gravity and matter in the low energy sector. Okay? So these wormholes are essentially very long. They are characterized by some total length L, and they are supported by a large number of matter inhomogeneities. Okay? And essentially the other length scale which characterizes the wormhole is the scale of matter inhomogeneities, which is this L delta. And we call these wormholes caterpillars for obvious reasons. Okay? And in the second part of my talk, I will show that the microstates dual to these kind of semi-classical states are actually very close to being typical EPRs of the two black holes. So I will quantify, using the gravitational path integral, a correspondence between a microscopic measure of how random the states look and the semi-classical, I will relate this notion to a semi-classical properties of the geometry, like the length of the wormhole. So in some sense, I will derive a correspondence between quantum randomness, holographic quantum randomness, and the emergence of the length of the wormhole in the black hole interior. Okay, so the goal is to start from the thermofield double, because the thermofield double is a state that we understand very well in holography, and from there try to build a generic entangled state of two black holes. The natural thing to do is to just take the thermofield double and time evolve it with some time-independent Hamiltonian. Okay, so this will produce a trajectory in this space of maximally entangled states in this example, in this qubit example. And essentially, we will end up with some time-dependent state whose wave function looks like this. So the basis which diagonalizes the wave function is essentially the energy eigenbasis of the Hamiltonian. And now it will acquire a bunch of phases. So this will make it more generic. And these phases will essentially be given by they will be characterized by the energy eigenstates, okay? By the energy eigenvalues. So it is, it is easy to see that this state will never become typical. The reason is that this trajectory that we are evolving our state with doesn't explore a generic point in Hilbert space. So essentially, the conservation of energy along the trajectory, the conservation of the Hamiltonian, prevents the trajectory from exploring most of the Hilbert space. So it only explores a measure zero subset of the space of maximally entangled states, and therefore this state never becomes a typical EPR. Okay. A way to see this is, well, it's pretty simple. One can just focus on the energy eigenvectors. If our Hamiltonian is a few-body Hamiltonian, this means that it only contains few-body interactions. The energy eigenstates are not random states, and therefore, as I told you before, a typical EPR has a random state diagonal form. So this state will never become a typical EPR, already for few-body Hamiltonians. But even if we consider completely non-local Hamiltonians or random matrix, then these vectors are uniform random states, but these phases will fail to incorporate the characteristic eigenphase repulsion of the eigenphases of a random unitary. Okay. And a way to see this is just, well, empirically, you can just take some time evolution operator at very, very long times for some random matrix here, plot the eigenphases. So here I'm plotting them at timescales comparable to the inverse mean level spacing. This means at timescales which are exponential in the entropy of the system. And you see that the difference is that the eigenphases tend to clamp on top of each other. So the eigenphase separation in this case is given, the histogram is given by a Poisson distribution. Okay? So this shows that the eigenphase repulsion is absent in this kind of state. Nevertheless, this kind of strategy to time evolve a thermofield double has been used in the past to try to explore the Hilbert space of black holes. And the idea is that if you time evolve the thermofield double, so thermofield double lives, the semi-classical dual lives in this t equals 0 slice. If you time evolve it forwards, then essentially what happens is that the wormhole in the black hole interior grows in time. Okay. So this already tells us that a more generic wormhole is a longer wormhole than the one for the thermofield double. Okay? This can be also understood from the fact that the thermofield double has very large correlations between the two systems. So it is a KMS state. Okay, and there's been ideas, following this logic, which relate notions associated to the time evolution, like its complexity and so on, to the geometric growing of the length in the black hole interior. And essentially the idea is that the length of the wormhole is related to some notion of complexity of time evolution, although nobody has been able to make this very precise. Okay. So, but my point here is that even at exponentially long times, as I showed you before, the state becomes sort of very, very complex. It's very difficult to generate it from a thermofield double. However, it doesn't become typical. And perhaps one way to see this semi-classically is that the wormhole becomes exponentially long, but it is still given by a vacuum solution to Einstein's equation. So a vacuum solution is sort of, which is also very symmetric, cannot be generic. Okay. Nevertheless, there's been a lot of recent work to try to understand this regime of exponential times, where some quantum gravity effects are supposed to take over. Okay? So what we did was to instead consider the evolution by time-dependent Hamiltonians. Okay, so our time evolution is now some time order exponential of some time-dependent Hamiltonian. And specifically, it will be convenient to choose a specific class of time-dependent Hamiltonians, which are called Brownian Hamiltonians. These Hamiltonians consist of a few, of a set of operators, which I will think of them as few body. So in holographic systems, this would be like single trace operators. Okay, and next to each operator, we choose some time-dependent coupling, and we sum over operators. Okay, this is the generic form of the Hamiltonian. And essentially, what makes it Brownian is that we are choosing the time-dependent couplings from a white noise correlated Gaussian random distribution. So our each coupling is chosen at random at each time step with zero mean, with a variance which is independent at different times. So essentially, the couplings are uncorrelated at different times, and the variance is controlled by some scale j that we define here. Okay. And the intuitive picture is that this time evolution, this class of time evolution, it will generate some sort of Brownian motion in the space of maximally entangled state when we apply it to the infinite temperature thermofield double. So this Brownian motion will eventually be able to explore the whole Hilbert space and generate a typical entangled state. And yeah, the Brownian Hamiltonians, they are sort of known in quantum chaos and quantum information literature because they provide a continuous version of what is known as a random quantum circuit, which is essentially a discrete time evolution, discrete time model where it is a model of quantum computation where the gates at each time step are chosen randomly. So here what we are doing is choosing the Hamiltonian randomly at each time step, which is a continuous version of that. Okay, so let me just tell you what the advantage of choosing this kind of dynamics is. The advantage is essentially that we can solve the dynamics on average exactly. And let me just illustrate this with what is known as the spectral form factor. I could do it with correlation functions as well, but let's just, for simplicity, consider the spectral form factor, which is some correlation function of the spectrum of the time evolution operator. Okay? So the spectral form factor is defined as trace of u of t squared and then average over couplings. The idea is that for Brownian Hamiltonians, one can write this down as an effective thermal partition function with some effective Hamiltonian, which is also known as the Liouvillean in quantum Markov processes. Okay, so the idea is that the correlations between couplings on different contours, so trace of u of t squared, each contour prepares trace of u of t, and there's random couplings on each contour. The average over couplings produces effective interactions between contours in the form of a time-independent effective Hamiltonian. The effective Hamiltonian contains quadratic interactions between the operators on both contours. Okay. So essentially, computing some very complicated quantity on average reduces to a sort of simple quantum StatMech problem. Another interesting property which makes this sort of solvable at very late times for a generic set of operators is that the ground state of this effective Hamiltonian is known. It is the infinite temperature thermofield double. And if the operators are generic enough, we expect the Hamiltonian to be gapped. We expect this ground state to be unique. And so we can, at very late times, this kind of quantity will be dominated. So T is just the inverse temperature. Late times is like low temperatures. This kind of partition function will be dominated by the ground state, which gives a 1 contribution. Then it will be dominated, the leading correction will come from the first excited states. So there's n star number of first excited states generally, and they have some energy E gap here. Okay. So we've computed the spectral form factor in a very generic way for any Brownian Hamiltonian. So this kind of form is very universal. Let's now compare it to what is expected for the spectral form factor for time evolution operators generated by time-independent Hamiltonians. So this is what is famously known as the slope, ramp, and plateau structures in the spectral form factor. okay, which essentially represent the fact that the Hamiltonian is chaotic, in particular the ramp is what represents the fact that the Hamiltonian is chaotic. But what I want to show here is that when we computed this value of 1 for the spectral form factor is essentially, what's going on? Is essentially, the value of 1 is essentially this very late time value. And we can compare this very late time value with the very late time value for the spectral form factor for a time independent Hamiltonian. And as you see, they are very far apart from each other. Particularly, they are exponentially far apart from each other. So this is essentially a manifestation of the fact that the Brownian evolution is able to generate the correlations of a random unitary, whereas the time-independent Hamiltonians are not able to generate that. Okay, so this value of the plateau essentially comes from the eigenphase repulsion that I was talking about before. Okay, so this is sort of generic. Let's try to apply this time evolution to holographic systems describing black holes. So the first problem we encounter is that, well, Brownian Hamiltonians, they are just time-dependent couplings. They will inject energy into the system. And so a black hole in ADS-CFT is a thermal state at finite temperature. So if we just naively apply the time evolution operator to a thermophile double, we'll end up with some time-evolved thermophile double with a bunch of matter shocks inserted into the black hole. So essentially, here I'm thinking about the operators that drive the Brownian evolution as local single trace primaries of the CFT. And so the semi-classical duals of those operators are just bulk matter fields, like supergravity fields in top-down examples. And so this will essentially inject a bunch of matter into the black hole, and the black hole will grow, and we will eventually lose track of the original black hole that we started with. So that's not ideal. Essentially, this is a continuous time version of what it was considered by Schenker and Stanford to study scrambling in black holes. Okay, but the point is that if we just do that for the time evolution operator driven by some time-dependent couplings, there will be a maximum time after which the back reaction will become very strong, and we will lose track of the black hole. This time scale is of the order of the entropy of the black hole divided by the number of perturbations. Okay. So we want to keep track of a equilibrium black hole for timescales which are much parametrically longer than that in principle. Okay, so the idea is essentially to time evolve the black hole with this Brownian time evolution infinitesimally, and then cool the state down with some Euclidean evolution. And do this sort of infinitesimally over and over again. And in this way, generate some finite temperature version of this Brownian evolution. So we will take the infinitesimal time steps of Euclidean and Lorentzian evolution to 0 while keeping t fixed. Okay. Formally, this operator can be written as some, path integral in the CFT along some complex time contour, which looks like this. Okay, it doesn't matter really what it looks like for this talk, but the point is that even though these time faults might look a little bit exotic, they are there to implement the interaction Hamiltonian where only the Brownian time evolution is important, and the bare Hamiltonian of the black hole is sort of not contributing to this kind of evolution. And what we will do is to prepare states of two CFTs just by performing the CFT path integral along this complex time contour. Okay, so this will prepare some state at time t for a single realization of the couplings. And given that we are considering random couplings, we will have an ensemble of states at fixed time t. Okay, so in holography, to try to understand the semi-classical dual, the holographic dual to a given microstate, what we typically do is to use the ADS-CFT dictionary, which tells us that we should compute the norm of the state at a Hartle-Hawking, and then evaluate the norm of the state using the gravitational path integral in the bulk with the boundary conditions given by the actual CFT data that we use to create the state. Okay. So of course, doing this for a single realization of the couplings for Brownian evolution is very, very hard because this is a time-dependent problem. In general, the bulk solution will not be real, and it's very complicated to consider the back reaction of matter and so on here. So a trick that you can use in order to elucidate coarse grain properties over the ensemble is just to take the average over the couplings. And again, the Brownian dynamics simplifies matters because the average value of the norm can be written as some time-independent quantity, in particular as the survival amplitude of the thermophile double state, time evolved with a Euclidean time-independent Hamiltonian by a time t. Okay, so this is sort of like more complicated version of the spectral form factor sort of simplification that I was telling you about before. Okay. In this case, this is a finite temperature effective Hamiltonian, so it's different than the infinite temperature one. And one can show that it has this form. So it has the previous form with quadratic interactions coming from the correlations between couplings correlated between replicas here. And then it has these additional terms coming from the fact that we're cooling the system down gradually. So these terms appear from the cooling. This class of Hamiltonians has been studied in ADS-CFT in the context of making wormholes traversable. Okay, so essentially, if there's a large number of perturbations, one can sort of very generically argue, if the Hamiltonian is chaotic, that this effective Hamiltonian contains a unique ground state, which looks pretty much like the thermophile double. And so time evolving with this Hamiltonian on this particular state does nothing. And so this thermophile double looking state semi-classically should be a connected spatial wormhole. And so the full space-time should be that of a traversable wormhole if we decide to evolve with this Hamiltonian. Okay. The point is that this Hamiltonian contains interactions between the two boundaries, and so the wormhole becomes traversable because of that. But for our purposes, we just want to compute this thing, this norm, the S-average norm, gravitationally using the gravitational path integral. Okay. We can do this very explicitly in low-dimensional models. So for instance, if we just think about the SYK model, where all of the states are states in the product of two SYK systems, we can write down, we can use the fact that this effective Hamiltonian has been studied in this context by Maldacena and Chi, to write down this norm as some effective classical problem for some, classical particle mechanics for some specific variable, which is L. So essentially, this is another formulation of JT gravity, which is related to the one that Samir reviewed in his talk. And the idea is that this L parameterizes the geodesic length between different boundaries. Okay, and it is a gauge invariant variable. So there's some SL2R gauge symmetry there, and this length is the gauge invariant variable that you should use when you have two boundaries. And so essentially the problem, JT gravity reduces to the particle mechanics of a Liouville wall. So it's an exponential potential. And so what happens is that this effective interaction, in this case, has been studied and introduces some other term. Okay. And so one can solve for this disk geometry very explicitly in that case. What happens essentially is that this additional term stabilizes the length between the two boundaries. And so the disk stretches for that reason. So essentially, the length is stabilized and there is some effective, some approximate time translation symmetry of the solution. And so the disk gets stretched. Okay. So the point is that one can, okay, we've computed, we want to compute the norm of the state. So this is the bra. Sorry, the bra is in the top half. The ket is in the bottom half. We're averaging over couplings. We're solving for the gravitational saddle point. So the semi-classical dual essentially lives on the time symmetric slice of this saddle point. And it turns out that for the reason that this length variable is stabilized and there is some time translation symmetry of the geometry, one can show that the analytic continuation of this space-time looks like a two-sided black hole with a very long black hole interior. Okay, so the length of the wormhole is essentially proportional to the circuit time that we use to prepare states, using the fact that this approximate isometry appears in the calculation. Okay, and one can argue that the same thing happens in higher dimensions using generic properties of the effective Hamiltonian, although in that case the calculation is much more complicated. And yeah, we didn't do it in higher dimensions. But the point is that this shows that the length of the ensemble of caterpillars is on average growing linearly with the circuit time that we use to prepare the states. If we want to just compute the slopes, we can essentially use the fact that the effective Hamiltonian is gapped in SYK JT gravity. This can be computed explicitly. Essentially, the first excited states are fermion excitations on the wormhole. And what happens is that one can use this information to measure length locally in units of the matter correlation scale. So this scale is essentially the scale of decay of the 2-point function for a matter operator, for the lightest matter operator on the wormhole. And this E gap is essentially the boundary energy times energy scale. So this relates the bulk quantities, length in units of this matter correlation scale, to the boundary quantities, which is the boundary time used to prepare the state in units of the gap of the effective Hamiltonian. Okay. So this is the geometry part of the talk. We'll now try to relate this length to some microscopic property of the ensemble of states. So the idea is that, as I told you before, if you just time evolve the thermofield double with the Brownian evolution, it will become more and more generic. So it will become more and more random, more and more typical. And one can quantify how random a state or an ensemble of states becomes in terms of the quantum information notion of a quantum state K design. So the idea is that a K design is an ensemble of states which reproduces the first K moments of the random state ensemble. So for K equals 1, that means that any expectation value that you take on this ensemble is on average given by the same value as the expectation value of the ensemble of typical EPR states. So in particular, this means that if you have a 1 design, the ensemble appears thermalized on average. So any state that you pick from this ensemble, which is sort of generic within the ensemble, will have equilibrated expectation values, given that the random states have equilibrated expectation values for any operator. So K equals 2 is a much stronger requirement. It just means that K equals 1 is true. So all the expectation values are given by the random expectation values. But moreover, the variances of the expectation values are also given by the random ensemble, as well as nonlinear quantities over states, which are quadratic. Like, for instance, the second Renyi entropy of the reduced density matrix to one of the two sides. Okay. So physically, this is a very strong requirement, even though from the quantum information perspective, this is natural. So already to have a 2 design is something kind of very strong. But yeah, we will try to study how this K of a K design grows in time in gravity. Okay. So at infinite temperature for this Brownian time evolution, one can show that very generally, very universally, this K grows linearly in time. Okay. So the ensemble of states that one creates using this Brownian motion becomes more and more random in a very quantitative way. So the amount of randomness grows linearly in time for that case. So the question is what happens in gravity, okay? So in order to do this, to try to compute K for black holes, we need to essentially compute the distance to a K design. And this is given in terms of some quantum information quantity, which is known as the frame potential of the ensemble of states. Essentially, the idea is that one needs to compute the overlap between two independent states of this ensemble to the power of 2K, and then take the average over the couplings. And this quantity is just a number that depends on time. It's a function of time. When this number is close to the infinite time value, then the ensemble is very close to a K design. Okay. So for K equals 1, we just need to compute the square of the average between two independent states of the ensemble. So this is just two replicas, each of which computes some overlap. We need to take the average of this thing over the couplings. And again, because of the Brownian couplings, the problem reduces to computing a quantum stat-mech partition function for some effective Hamiltonian coupling the two K replicas together. So this is a more complicated version of the things that I was talking about before, but one can sort of write down this quantity as some quantum stat-mech partition function at inverse temperature 2T. And the idea is that this effective Hamiltonian, at very long times, this quantum stat-mech partition function will be dominated by the ground space and the first excitations. So very generally, one can show that, well, essentially what happens is that the low energy sector of this effective Hamiltonian breaks replica symmetry and is dominated by k copies of the 2 replica effective Hamiltonian. So essentially, the whole problem in 2k replicas reduces to an effective problem in 2 replicas. Okay. So in gravity, yes, thank you. This is manifested from the fact that we can compute this kind of thing gravitationally using the gravitational path integral, and the dominant contribution at late times comes from a 2-boundary wormhole. Okay, so one can compute the frame potentials for holographic systems using the gravitational path integral, get an expression at late times that looks like this. So essentially, the frame potential is the infinite value, which counts the number of ground states times 1 plus the first excitations of the 2 replica effective Hamiltonian and some exponentially decaying function of time. And this allows us to compute the distance of the ensemble of states to a k design and show that it decreases exponentially in time. And essentially, the number of ground states scales exponentially with k because there's this k factorial. And so one can impose that eventually at some time tk, the distance is smaller than epsilon, and so the ensemble of states becomes an approximate k design, and show from this kind of formula that k for gravity grows linearly in time with the slope given by the gap of the 2 replica effective Hamiltonian. So this is a sort of very general argument, but it works in gravity because of this 2 replica wormhole, which can be explicitly constructed. Okay. So what we showed here is that randomness grows linearly with the same slope as the average length of the wormhole. So combining both linear growths, we get our main result, which is that the ensemble of caterpillars of length L and matter correlation scale L delta forms an approximate quantum state k design of the black hole for a k which grows linearly in L over L delta. Okay, so let me just emphasize this. This relation is a relation between some microscopic property of the ensemble of microstates, which is this k, which is the randomness that they have, so how random they look. And on the right-hand side, we have a quantity which is purely semi-classical. It's just the length of the wormhole. And so this constitutes a complexity geometry relation in holography, but which has been derived from first principles using the gravitational path integral. So this linear growth of k has been computed. So let me just end with general remarks and with some discussion. So the ensemble of caterpillars that we constructed, we show that they provide a window into the generic structure of the Hilbert space of black holes in any gravitational theory which contains matter. Okay, any gravitational theory which contains matter, you can construct these states, and in principle, if this theory can be non-perturbatively completed to some holographic theory, these states are supposed to be generic states in that Hilbert space. So there's many open questions from our constructions. One of them is whether the caterpillar states contain firewalls or not. So because there's been this discussion in the literature of whether typical states of black holes contain firewalls. So firewalls in this case, they would correspond to very highly boosted matter shocks, which are hugging the black hole horizon and which collide with the black hole, so collide with the infalling observer once the infalling observer crosses the horizon. So it's not clear whether these caterpillars, which are just, the slices of the space-time, when you evolve them, they develop these kind of firewalls. Particular, there's been recent claims in the literature or proposals saying that half of the typical states should contain firewalls. So there should be half of the caterpillars in principle which contain firewalls. Okay. There's also the issue of reproducing signals explicitly, like the signal of the left-right correlation function for some operator. That's non-trivial of whether the caterpillar saddle point is the dominant saddle point in that case. So it would be nice to get this kind of analysis done. Another interesting problem is whether we can form K designs of black holes in other ways than just, adding matter in the black hole interior. And this relates to, the ways that people in quantum information generate K designs, which could include performing measurements or LOCCs. In particular, this relates in holography to the ideas in these papers by Malacena Kurkulu and by Jan de Boer and friends, where they they start from some thermophile double state, they do some measurement on one of the two systems, and they end up with some more generic state with some end of the wall brane in the interior. So this kind of thing could also serve to form K designs. It would be interesting to study the relation between the two kind of states. Okay. Let me just end with some very generic comment. So the matter that forms the caterpillar eventually falls into a singularity. So we've characterized more generic black hole microstates in terms of their semi-classical geometry. This would be telling us that the singularities that these states have are also more generic from the microscopic point of view. So it will be interesting to relate this genericity between the microstates to the genericity of the singularities in the form of some BKL kind of analysis. Okay? So this is all that I wanted to say. Thank you very much for your attention.
Hi, thanks for the very clear talk. There's one point which is not clear to me. Why do you call these things semi-classical? If I understood correctly, you have to average over the Schwarzian to get the results in what you call the geometric picture.
Right. The point is that these couplings are semi-classical. So
yeah, but the calculation is in the quantum gravitational theory, right? In order to reproduce. Okay.
Yeah, it's just that we're doing saddle point approximation to every quantity after averaging over couplings. We're just taking the leading saddle point, and that's.
No, I mean in the bulk, you're using the. You have to do this calculation of Maldacena and Franz. That you have to average over the. You have to calculate a quantum expectation value in the Schwarzian theory.
Right. Yeah.
So the early time behavior of the spectral form factor typically shows a random matrix universality, which is a smooth power law decay. But the plot you showed had some sort of oscillation in the slope region. Could you perhaps
well, that depends on the
on
ensemble, right? Like for GUE, you get this. You mean like the black line?
Yeah. That's sort of the oscillations that you have.
See, this is some Bessel function that you get from GUE, like for the average density of states. If you Fourier transform that.
I see. Yeah, typically it's like 1 over t cube from the Wigner semicircle or near the edge.
Yes, you're right.
But here probably it's because of the ensemble, specific ensemble that you're considering.
Yes, you're right.
Okay,
thank you.
Thank you very much.
So you showed this linear growth of the wormhole, and let's believe that it's related to the complexity of the boundary state. So from qualitative arguments with system of qubits, it's understood that at very late time it should saturate at a certain point, but very late, so exponential in the entropy. So I was wondering whether you see something like that, or you have an argument in your description for this thing to happen?
Yeah, that's a good question. No, we cannot access that regime like within our semi-classical sort of. We're using the gravitational path integral within the disk approximation. We're not doing anything non-perturbative or anything like that. So yeah, it would be interesting to see whether randomness saturates as complexity. Yeah.
Okay, then thank the speaker again. And now there is the coffee break, and we reconvene at 11:50.